Lesson 88 is called Exponential Growth and Decay. We have already touched on this a little bit, so thinking about exponential functions, what does that make you think of? In class, we talked about exponential functions a few months ago, and we talked about the guy who had 1 grain of rice and then he doubled it every time and he ended up with mountains of rice. That's an exponential function. And whenever you see the word exponential, you know you're going to have E in it. So exponential growth and decay is a certain type of function that has certain variables that you're dealing with every time, and it's either growing, which means it's starting from a point and going up exponentially, or it's decaying, which means starting from a point and going down exponentially. And there's a formula that you just have to memorize for exponential growth and decay. And that formula is A sub t equals A sub 0 e to the k t. And each of these variables means something. So this is just your formula that you need to memorize. Here's what they mean. A sub t means amount over time t. So whatever your time amount is, this is what you're going to end up with. A sub 0 is your initial or original amount. It's how much you're starting with. With the rice example, it would be 1 grain of rice. Whatever you're starting with, that's your starting point, your original amount. E is just E, it's nothing special. K is going to be a constant, just like it is when we do direct and inverse variation. K is just a constant. And then T is going to be time. So this is your exponential growth and decay model. And these are the values you're going to get. These are going to be word problems. They'll give you some of the values. You have to figure out other values. One last bit of information before we start doing examples. K is what tells you whether it's growth or decay. If K is greater than 0, so if it's positive, then it's going to be exponential growth. Likewise, if K is negative, you're going to have exponential decay. And that is all of the information you need to know to be able to solve these problems. So let's do a few examples together now. Example 1 says, the number of bacteria present at noon was 400, and 9 hours later the bacteria numbered 800. Assume exponential growth and find the number of bacteria present at noon the next day. Sketch the curve. All right, there's a lot of information in this problem. So first things first, we need to make sure that we organize what we're given at the beginning. So this part right here has all of your important information in it. It says, the number of bacteria present at noon was 400. 9 hours later, the bacteria numbered 800. So we're assuming that this right here, the number of bacteria present at noon, is your original amount, 400. So we know A sub 0 is going to be 400. Then 9 hours later, that's going to be your time. We're assuming the time elapsed is 9 hours. Then it says after the 9 hours, the bacteria numbered 800. So A sub 9 equals 800. So the amount of after 9 hours is 800. Okay, so then it says assume exponential growth. So we know K is going to be positive, and find the number of bacteria present at noon the next day. We can't do this yet because we don't know what our constant is yet. So first we need to find K before we can move on to the rest of the problem. So we'll use our equation. AT equals A0 e to the KT. AT is going to be A sub 9, so that's going to be 800. A sub 0 is 400. E to the, I don't know K yet, and then T is 9. Then we can solve. Divide both sides by 400. So you'll get 2 equals e to the 9k. Now, k is in my exponent. Every single one of these problems, I don't want to say every single one, most of these problems, you are going to have to do the natural log, ln, in order to get rid of e so that you can get to the exponent. So what we're going to do, so ln, because k is in exponent. So what we're going to do is we're going to take ln of both sides. Ln of 2 equals ln of e to the a, oh, that's a 9, to the 9k. What that does is my ln and my e cancel out. And I'm left with ln of 2 equals 9k. And I can just type that into my calculator. So if you do ln of 2, and then you divide it by 9, you should get 0.077 as your k. That should line up with what it says. This says exponential growth. We have a positive k. We're good. All right, so now we need to find the number of bacteria present at noon the next day. So what would the time elapsed be? My original amount is going to stay the same. My time is going to change. My amount is going to change because it wants to know the amount. My k is going to stay the same. So what would my time be? If I'm starting at noon and then I want noon the next day, my time would be 24 hours. So what I'm going to do is use all my information and plug in to figure out what a sub 24 would be. So I use the same equation. A0 is 400. E, K is 0.077, and T is going to be 24 hours. And this right here, there's nothing missing. I can just type that into my calculator. 400 E, make sure you use parentheses, 0.077 times 24, and you should get 2,538.8. We can just round that to 2,539, and that would be your answer. Example 3 says, the amount of substance initially present was 400 grams, and after 90 hours, only 380 grams remained. Assume an exponential decrease and determine the half-life of the substance. Make a sketch of the graph. All right, the amount of the substance initially present was 400 grams. So that goes ahead. We know that that is our original amount, 400 grams. Then, after 90 hours, T equals 90, only 380 grams remained. So A of 90 equals 380. Assume an exponential decrease. Determine the half-life of the substance. Half-life, what that means is, when is half of the substance left? So how long does it take? What's the time? That would mean 200 grams were left instead of 400. Before we can do that, we've got to figure out our K because that's missing. So A sub 90 is going to be your 380 equals A sub 0. We were using the same equation, E to the K times T, which is 90. And we've got to figure out K. So divide both sides by 400, you should get 0.95 equals e to the k times 90. And then take the ln of both sides. I'm going to switch 90 and k so it looks a little better. Ln and e are going to cancel out. And then you just divide both sides by 90. If you do that correctly on your calculator, you should get negative 0.00057. And it should just line up. It says exponential decrease. We should have gotten a negative k. Perfect. So now we want to see what the problem wants. Determine the half-life of the substance. So what you're doing when you're determining half-life, it's the time when there's half left. So we're looking for a time when it says half-life. So we'll still have the same A0. We know that A of t is going to be half of A0. So we'll have 200 is the amount left. My original amount was 400. E, my K is the same, negative 0.00057, and my T is what's missing here. So now divide both sides by 400. You're always, when you're looking for half-life, you're always going to end up with a 0.5 over here. It's how it works every single time. Negative 0.00057 T. And then you're going to take the ln of both sides because T is in the exponent. So ln of 0.5 equals, it's going to cancel out with the E, negative 0.00057T. Do it on your calculator, divide both sides. T equals 1,215.79 hours. All right, and then the last part of this problem says to make a sketch of the graph. All you have to do when you sketch these graphs is, you can always just do the first quadrant. You're going to sketch the starting point at y, on the y-axis, and that's 400. And then if it's exponential increase, you'll just draw it going up from there, but this one's exponential decrease, and that is all I want. I guess you could label this axis is going to be t, and this axis is going to be a of t. Do that as well. So this is what I want when it says sketch the graph. Example 4 says, a radioactive substance decays exponentially. After 100 years, 500 grams is left, and after 200 years, only 300 grams remains. Find the amount of the substance that was initially present and its half-life. All right, let's look at our original information first. After 100 years, so A of 100, 500 grams is left. So A of 100 equals 500. After 200 years, A of 200, only 300 grams is left. So here we're given two final amounts. Find the amount of the substance that was initially present. So find A of 0 and half-life. So that would be the time when half of it's left. All right, so this is an interesting problem because we're not given A of 0. So let's write both of these as equations. So A of 100 would be 500 equals A sub 0 e to the k, and our t is 100. And then A of 200 would be 300 equals, same initial substance, but we don't know how much it was. That's what we have to look for. E to the k, it's going to be the same k, we just don't know what it is yet, times 200 is our time here. All right. We have two variables that are missing in these two equations. The way we're going to solve it, it's the way exponential functions work, and it's kind of weird, we haven't done it before, is we are going to divide the two equations by each other. I'm going to take, you could do it either way, I'm going to take the second one, and I'm going to divide both sides by both sides of the first one. So 500. All right, so I've divided this whole second equation by the whole first equation. I know it's weird, but look what it'll do for us now. 300 divided by 500 is going to be 0.6. A of 0 cancels, and e to the 200k, so this is the same thing as e 200k over e 100k. Those can cancel, and I'll be left with e to the 100k. Well then, if I take the ln of both sides, my ln and my e cancel. ln of 0.6 equals 100k. Do ln of 0.6, divide by 100. You should get negative 0.005 as your k. All right, so that's our constant. Now we can actually plug it back into either one of these equations to figure out our original amount. So let's just plug it into the first one. 500 equals A0 e to the negative 0.005, 100 is our t for that one. So we'll do that on the calculator, divide 500 by whatever this is. If you do it correctly, you should get 824.36 grams as your original amount. Then, the last thing, so that's one of our answers right there. The last part of the question says, find its half-life. So then we're going to be looking for t. We want half of 824.36 to be our final amount. And we want our original amount to be 824.36. E to the k, same k. And then we don't know the t because it's half-life. We don't know that yet. The reason I wrote it like this is because, look, if I divide both sides by 824.36, it's going to go away, and I'll be left with my 0.5 over here, which, like I said, happens every single time you're looking for half-life. E to the negative 0.005 t. Take the ln of both sides. And then if you plug it in correctly, your t should be 138.63 years.